And the approach I am going to give is very, very different. Yeah, please. And it's not a textbook material, but I look at it very differently, how the materials are formed from molecules. Okay, just this is basically, the people who have been instrumental in making this particular technique called crystallography. Because today, when you have a crystal and you need to have the crystal structure, and we go one step forward, that once you get a crystal structure, it's not, you don't look at only one structure, but you see a series of structures. Now using a thing called a database, crystal structure database, Cambridge Crystal Structure Database is available to the whole community. And so you look at a series of structures and then try to look for pattern, and then go back and then look at the way the reaction has taken place. Because till today we are not in a position to really monitor the reactions when the molecules are interacting and then forming finally a crystal. So this is a major problem. Okay. Now, since I grow with this particular book on structural chemistry by A.F. Wells, I want to quote him. He is almost a Bible for inorganic structures. At different stages in the development of chemistry, various compounds or groups of compounds have appeared to be anomalous as regards either their formulae or properties. When the appropriate advance has been made in, say, the theory of interatomic forces, or when a new technique has led to further information about the relative positions of atoms, it has become evident the anomalies were simply indications of an inadequate understanding of the structures of the compounds in the wildest meaning of the word structure. Now, most of us, when we are taught, at least in this country, I am very clear because I have been teaching for the last 27 years, and even now I am a student, and the structure means different people look at it differently. So I will make it simpler. Most of the time the chemist is looking at the structure only in terms of the molecule. But here we are going to look at assembly of molecules, and the molecules which give other supramolecules or a supermolecule, which we call it as a crystal, gives you a diffraction pattern when it is exposed to X-rays. And basically what you do is you assume a particular model and then extract that structure. So you have to be very clear when you finally solve a crystal structure, it is only with respect to a model. How good your model is, how reliable your model is something one have to keep it in mind. Many a time you can go wrong. So this is something which you keep in mind. Now I'll come to this now, this particular approach, what we call it as a crystal engineering. Mostly it was developed for organic solids for the last 40-50 years, for the last 4-5 decades. But now the crystal engineering is just do everything. But for convenient, we will only talk about small molecules. We will not talk about macromolecules because that will be beyond the scope of this particular talk. Now, crystal engineering is the understanding of intermolecular interactions in the context of crystal packing and the utilization of such understanding in the design of new solids. Because till now we mix something, we get a crystal, and then later we try to analyze the structures, and then we try to compare with the kind of reactions we were doing it, and then we try to rationalize it in different ways. But it is very important that if you want to design a new crystals, the crystal having certain components, then you need to understand a pattern, and that is what I am trying to tell you over here. A crystal is a very precise and specific type of molecular assembly. Eventually, it's all the assembly of molecules. But now what happens is many a time you have to encounter very commonly two types of crystals. One, the assembling species are essentially molecules. I'll give you examples and then I will discuss about it. In another cases, you suddenly lose the actual molecules. You see only atoms and ions or whatever it is, but you don't really see the kind of molecules that you normally visualize in a typical a chemistry, whatever you are being taught. So you have to just keep in mind, but I will come back to it. So a crystal is a very specific type of molecular assembly. Crystal engineering teaches us how to bring these molecules together exactly as we want. But still we are a long way to go from actually taking a particular models and then really it's like a Lego toy you can think of. You have different species and then connecting together and finally getting it. Now here, to grow the crystal is still an art. But there is a lot of science involved in that. So don't consider that it is just an art, it's magic. But there is still a lot of science here, but you have to pay attention to that. That is the one or two things which I want to bring you today. And you have to realize that crystallization is a supramolecular reaction. Now, this is taken from our book, Crystal Engineering, a textbook, which was published 6 years ago, 2011, Cambridge University Press. So those who are interested, you can go and look at it, or you can write to me. Now here we have given a distinction between a typical molecular synthesis that the student most of the time have been taught, like in your earlier classes. Most of the time we deal with only molecular synthesis. So when you deal with the molecular synthesis, essentially you look at only the chemistry around a few atoms. Invariably, the number is very small, very finite. And most of the time, if you are dealing with an organic molecule, that is a covalent bonds. But if you are dealing with an inorganic molecule, then you have sometimes both covalent bonds and coordination with bond. Then the synthesis is essentially, you call it as a molecular synthesis. You come across isomers, you talk about transition state, you also deal with the reaction around one or few atoms. Most of the time this is what we are being taught. Now when you deal with the crystalline material or a crystal, if you are dealing with it, then you need to think beyond the molecules. And to borrow Jean-Marie Lenz's phrase, it's chemistry beyond molecule. Many a time people call it as a supramolecular chemistry also, but different people use supramolecular chemistry in a different way, but that doesn't matter. And here, instead of looking at one bond, what we are looking at here is essentially the intermolecular interactions. Because you have more than one molecular species, and these molecular species are coming together and then trying to aggregate. Now, how many such molecules you require to define a crystal is still a question mark. You require 10 molecules, you require 100 molecules, or you require 1,000 molecules, or few thousand molecules to actually define a crystal. This is something which you have to keep it in mind. So here we are interested in the intermolecular interactions. We call it as the intermolecular bond. Now here the synthesis, we call it as you can call it as a crystal engineering or crystal synthesis, whatever you call. Just like isomers, here you come across a term called polymorphs. If you take carbon, you take assembly of carbons. The carbon can be assembled in the form of a graphite, diamond, graphene, which is a discrete molecule, and the molecules are interacting through non-covalent interactions, non-bonding interactions. You understand? If you look at graphite, on the 2 dimensions, the interactions between carbon and carbon is covalent bond, and you call the carbon as sp2 hybridized, and it is extended. Extended means infinitely. If you look at diamond, then you look at the carbon in terms of the sp3 hybridized carbon. Carbon-carbon interactions are still covalent, but it is 3-dimensional, and the interactions gives rise to a cubic structure, which you all know. When you consider fullerenes, C60, then you have a discrete cluster, right? Now each cluster, now you have a discrete molecule. These molecules interact through non-bonding interactions, non-covalent interactions. You understand? These non-covalent interactions are invariably weak interactions. It can vary anyway from a small energy to a large energy. So later I am going to tell you how these kind of non-bonding interactions essentially dictate and how easy or difficult it is to essentially play with these non-bonding interactions. Okay, now you have a transition state when you are dealing with one particular molecule goes to another molecule. When you are doing a few changes around a few atoms, you call that as a transition state. You are familiar with this. Now here we will call it as a crystal nucleus, something very similar to them. I will show you with a cartoon now. So here reaction, normally when you talk about reaction in a molecular synthesis, here we call that reaction is nothing but a crystallization. Okay, so crystallization is invariably a supramolecular reaction involving intermolecular interactions. Okay, how you can control it is a major thing. Now you just look at a typical diagram. You know, when you are dealing with the material synthesis, you would have looked at a diagram something like this, where you have an activation barrier, you go from a reactant to a product. Now here you translate the same idea but slightly differently. Over here this corresponds to essentially the reactants which you are putting it in a whatever it is, in a beaker or in whatever, wherever you are doing the reaction. And then it goes through a barrier and then you form the crystal. Pay attention here. So here this activation barrier, you used to call it as a transition state when you are dealing with the molecular synthesis. Here you can call it as a supramolecular transition state, because you are now considering not one molecule, a reaction around one molecule, but you are considering a reaction in which several molecules. What are those molecules is something which we may have to look at it depending on the system. That's going to be a little, that is a catch. So the different molecules, they come together, they try to assemble through different kinds of interactions. The interactions are mostly non-covalent interactions, but they can be a variation. It can be a hydrogen bond, it can be a van der Waals, or it can be different types of hydrogen bonding interactions, or it can be a coordination interaction also. Right? So when such things occurs, you can have different pathways. What it shows over here is you have two different pathways, and we call it as a supramolecular reaction pathways. Right? One pathway leads to crystal 2, another pathway leads to a crystal 1. Now if you look at it, basically this energy diagram, the profile, now one has lowest free energy in comparison to the other. So you can call this, suppose in a particular system, if this is the lowest free energy, you call it as a thermodynamic crystal, and the rest of them are all kinetic crystals. Many a time when you get a crystal, unless and until you know exactly what it is, because we don't, most of the time we won't know the energies, and calculations of the energies for a crystal is going to be a little difficult, is more involved. So you call all of them to start with, this is kinetic crystals. So most of the time when we grow crystals, if we don't know anything about a particular system, we will call it as a kinetic crystals. But in a simple cases like carbon, let's say, then you know that under these conditions, graphite has the lowest free energy, so that is the most stable system. So that is thermodynamically stable phase under these conditions. But if you go to a different temperature and pressure, then diamond will have the lowest free energy, so that will be the thermodynamically stable phase, right? But most of the time we talk about the other reaction conditions, then you know what you are talking about it. But these are all equilibrium phases. Sometimes you may get non-equilibrium phases also, but let's not talk about it. Now there is another thing which you have to keep it in mind, but here one issue remains is what actually triggers the nucleation of a particular crystal. Right now we don't have any experimental setup or any way of really realizing which way the reaction goes and what is that triggers the nucleation of a particular crystal, whether it is a 1 or 2. Many a time it's a hit and trial only, right? Even though people talk about in situ crystallization, when you say in situ crystallization, when you are taking about diffraction pictures, invariably after the climax has taken place, meaning either you have crossed over this particular barrier this side or crossed over the barrier that side, right? So we really don't know. It's the spectroscopic, because most of the spectroscopic data are from a dilute solution. But what you have to remember is a crystallization occurs invariably from a supersaturated solution. That is the diagram over here. It's typically, you do crystallization from solution. So solution, only when you exceed the solubility limit, then the crystallization occurs. That means crystallization occurs in the metastable zone, right? And you can also think of this dotted lines indicate it varies from system to system. You really don't know. This is a window. The window varies, and you also know that solubility is a function of temperature, so that also varies. This is only a crude graph. It doesn't give you. For different systems, it may differ. Okay, here you are undersaturated, so no crystallization will occur. Here you are in the metastable region, that is where the crystallization occurs. And if you are exceeding this particular dotted line, that means immediate precipitation will occur. So we are talking about the crystallization of a particular nuclei, a single crystals. So invariably that is obtained from here. Many a time you really don't know where you are operating it. It's only a triangle, right? Now, yes sir.
So,
yeah.
So you are saying that if we can change the temperature, we can lower the temperature, we can get the crystal 2, or we can go get the both crystal.
See, first thing is you have to understand this is the equilibrium line. This one. Here.
Yeah.
Here, this you consider this is the reactants.
Yes.
I will take an example, later probably, then you can come back also, you can see. No, still. So here when I say reactants, we are talking about the molecules which are assembling it. It's not that whatever you have put it in the solutions. You understand? So that is where I said that we will take an example and then we will come back to it if necessary. Right? Okay. Now here I want to define a term called a structural landscape. Now what exactly is the structural landscape? Provides a framework to compare the most easily accessed structures in a given system. Again, I am going to show it with only one example. I am going to take a simple example that you have studied in your school, college. No, you don't need any fancy examples. Then, we use different crystallization methods. You use different methods. You just mix it in a beaker and then do it. You heat it in a hydrothermal apparatus. You do it in a microwave. You do it by just grinding. So, in principle, you can obtain crystals by different ways. But what we are looking at it is that when you are accessing the different structures, then you are trying to compare their energy. Okay? Again, I will explain it in a minute. So, the different crystallization methods basically indicates you have different supramolecular pathways and the transformation of interacting molecules into a crystal. So, we are talking about only one set of interacting molecules. Things can change. Again, with examples I will show you. Now, retrosynthesis, it is a term which we have borrowed. I use the term by the famous, the Nobel laureate, an organic chemist, who coined the term retrosynthesis. E.J. Corey, right? So, Corey has given it for organic molecules. That is the term which it has been borrowed in the supramolecular chemistry literature. So, essentially, when you have a crystal, you dissect it. You literally break it into molecules. Molecules may be hypothetical, but molecules which are reasonable, chemically viable, and then how they are likely to, assemble through simply a condensation process. I will just come back to it. Then you can explain the occurrence of polymorphs, isostructures, hydrates, solvates, etc. The pseudo-polymorphs is a term which is not really accepted, but still geologists still use it along with the related structures, but then in a phase diagram. Many a time today, very few people look at the phase diagram. Actually, phase diagram tells you what? Phase diagram tells you the equilibrium phases in a particular system. That's where I gave the example of carbon itself, or you can take water. If you consider water, you don't look at the solid state structure, you only look at solid, liquid, vapor, the stability of the phases at different pressure and temperature. In the same way you can do for solids. Solids is convenient to look at, carbon, diamond, graphite and the liquid form of carbon. And you will notice today carbon, if you look at it, fullerenes are there, nanotubes are there, but they don't occur in the phase diagram yet. Right? So keep that in mind. So it is important to look at the phase diagram.